Ladies and gentlemen, we are going to talk about SolEngCo innovation idea. We all are engineers here, and we have to think in our design not only about the technical solution, but also about the economic aspect. You know that these days, in the tendering process for CSP plans, the bids are mainly evaluated on LCOE. SolEngCo team, under leadership of George Brackman, look at the possibility to optimize the parabolic solar field, which I am going to present to you now.
From the solar field, and we will look for the optimum. We will look at firstly at the theoretical assumptions, means that the sky will be clear all over the year. Then we will show you an example of the real side, because real life is different from the theoretical. But with our theory, we cannot go to the real world because we are not prepared. As you can see here in the context, so we will definitely talk about the orientation of the collectors, about the solar multiple, the optimization of both, and we will look for the most suitable solar field layout, combining the solar multiple and the orientation of the collectors, without thermal storage. That will be not presented here. This picture is very well known, but it is very important to understand it. So please allow me to repeat the very well known situation. I will use this paper as a parabolic trough collector, and I will track this collector from east towards west. But sometimes I will also track it from the south towards north. So for the thermology, we will talk about sun path, and we will talk about parabolic mirrors or parabolic collectors. This line seems to be clear to everybody, but let me explain. Firstly, we have a clear sky. This is the clear sky, and even we discuss here why 1000 watt per square meter have been chosen for the reference case. Because we have on the planet very nice places at which we can reach such a high irradiation. For our presentation, we choose the irradiation 900, 500, 950, which is a very high irradiation. As you see, from 7 to 17 o'clock, it's a very nice shape of the sun irradiation. And we will take a look at the collector from my side. I am on the north, looking down there to the south, and I will track it from the east, which is here, towards west. And you can see all the day we have a sun. That will change in our presentation. Now we are going to calculate the heat which we are going to gather from the solar field regarding the irradiation. As you can see, the irradiation is clear, and we will gather this shape of the heat coming from the solar field. I'm expecting now the rising many hands and saying, hey Miroslav, hey, I read in your presentation 78% of performance, and here you have a much less. And unfortunately no hands, so we will continue. So we will plot this line for the orientation from north to south. Okay? So this is this collector. We have a sun in the morning, noon, and in the afternoon. We are tracking, and every with the DNI is going up also the heat which is coming from the solar field. So from the solar field is not continuous income of the heat, is the mirrored the irradiation. So far so clear. Now we will do the same for on the same side for the same irradiation. If you can see here, we are on the latitude 30 on the northern hemisphere. All the day is perfect weather, which we can see also from this line. We put the collector from this in this position, and the sun is coming from here to here, and we track only this angle. As you can see, we plot this line. This one is from the previous one, the red one which we have seen, and this one is from this orientation. Already here you can learn that we get much more energy in the noon, you see, than if we would have the collectors in this orientation. Please be aware that we have a still solar multiple 1. Mr. Lee said it perfectly, because she said, Mrs. Lee said is, we have a solar multiple is all the energy which is coming from the solar field will be utilized at the steam turbine. So it's all the energy which is coming here, and if we can accommodate it in the power block, we will definitely get here much more power. In other words, if we will design the steam turbine from this point, then this orientation will definitely bring higher output in the noon, but no output here and less output here. It's clear. Now we will do orientation of the collector from the east. So it means we will put the collector on this side, which is southeast. We call it southeast. So here is the sun coming. In the morning is the dawn. It is sunset, and we put it oblique, as you can see here. Not this direction, not this one, but oblique. In this case, the sun arises, even if we are here, the incident angle is very high, so we will have higher losses. But in the evening, we will be facing more the sun, the cosine effect will be lower, and therefore we will gather more energy. That is shown here. So in the evening, we get more energy from the solar field than in the morning, to compare it to this orientation. The same is valid if we put it in this, if we put oblique in this position. Then we will gather more energy in the morning and less energy in the evening. Because here we are facing the sun. Here we have a very high cosine effect, which you can see here. We plotted this line. So far, so clear? But let me summarize. In this picture, we are going to show you all plotted energy coming from the solar field for all orientation. This, as well as this. So you can see we put the collectors in every direction, and we plotted the curves. From these curves, you see the highest could be this one. This one is more interesting for morning. This one for the evening, and the red one is collecting energy early in the morning and late in the evening. There was solar multiple 1. But we usually do not design for solar multiple 1, therefore this example for solar multiple 1.5. That means that if the energy is exceeding here, we are going to defocus some collectors because we cannot accommodate it in the power block. And in this case, we see that the red line and the blue line, they had here advantages for the blue one here and for the red one here. The dotted line, they shows the same, that either you gain more energy in the morning or you gain more energy in the evening. Clear? Let us show it in the frequency distribution load factor. Load factor is what is coming into the power block. So that's or what is leaving the solar field. For orientation east-west, this is the blue line, which you can see here, and you get more hours in the maximum load, if you can see here, but not so long over the year. So you get less than 3,500 hours operation. In the case of the orientation north-south, you get less hours for full load, but longer hours over the year. Now we will plot the annual solar heat which we get. That's the reference case which we have, solar multiple 1 for this orientation, 180, which is this orientation, and there will be the reference point. If we are putting oblique, we get more and more energy, if you can see. Here, doesn't matter if we plot it on this side or on this side. So one side is this, and the another side is this one. So we can gain 3.5 3.8 more energy from the solar field by putting the collectors oblique. For example, in this case, we have a 0, 100%. If we put it in this 135, we get 1.4% more than here. And if we put it here, we get 3.8 more. For solar multiple 1. Understood? And now we plotted for you the step for solar multiple 0, 1. As you can see, and we also plotted here the oblique. So the longest here time for 100% is for this orientation. Do we agree? Lowest for this orientation, the red one. Also the arrows are here for the blue one lower than for the red one. However, the overall annual solar heat collected from this position to this position is lower, the difference, from 3.8 to 3. Also this table is showing here the difference in the load factor. For 20 we get load factor higher for this orientation and more annual heat over the year. Here is the difference smaller as well as here. Let's go with the solar multiple 1.3. You can see that these lines are going closer, and here we get also less energy by oblique position than from this one. You see, even 0.5% calculated is less than here. But if we put it here, we still get more. Let's go for next solar multiple. The solar field is larger, and we can see that by this solar multiple, this orientation from north to south is the highest from the entire calculations. If we calculate further for multiple 1.7, the difference is even larger. So therefore this position of the collectors is much better. That's the reason why all the plants have this orientation. Not that the gain of energy would be this one for solar multiple 1, but already by solar multiple 1.5 is this orientation better, or even by solar multiple 1.7. As you can see here, we have a 3.5% less. One more for 1.9, we are close to 2, multiple solar multiple 2, you see that the difference is very large, already 5.2%. Do you see the connection between solar multiple and the orientation of the solar collectors? That's good. So if we put it into the calculations, so we talk about the gain of the energy. Here we plotted it from north-south and from east-west. The other red one is from north-south, that's this orientation, the full one, and the dotted line is for this one. So, as we know, we get always more for the dotted one at this point, and here we have at the break point, which was 1.3, 1.4. And then we get always more energy from the orientation north-south than from the oblique position. If we take a look at the price of the solar field now in capex calculated is not 100%. If you make solar multiple 2, doesn't matter, it's not appropriate to double so much price for the entire plant, because the solar field costs approximately 50% from the entire cost of the project. Do you agree with me? If you make solar multiple 2, you have to make double so big solar field, clear. But the cost of the entire CSP plant is not double so much, it's only 50% more. Depends on the ratio between the cost of the power block and the solar field, it's true, about approximately 50%. And it's also linear, so the larger it is, the more collector. So it's easier to calculate, it's a linear dependence. Then you calculate the LCOE. So it means you have a higher capex cost, but you have also more energy. So altogether, the capex costs are going to have this shape. So firstly, if you go with the solar multiple 1.2 or 1.4, you see that the effect of this combination is much larger. So the LOC is going to drop. But certain solar multiple is the opposite. So you go again back to this direction. And definitely, if we compare this orientation with this orientation, we see the breakpoint. And if we have a disorientation, then the LCOE is going up because the price of the solar field, the heat from the solar field is going down. So therefore, this LCOE is going up. Understood? So here summary. So larger solar multiple, larger solar field. Clear. Increase the factor of annual heat, solar heat. Of course, the higher is the solar multiple, the more energy we get from the solar field, because it's larger. Increase power specific investment cost. We have seen it here. So more energy, more cost. And decrease levelized cost of energy. What we have seen here in this, here a decrease. Definitely we have to find the optimum, but generally there where we are calculating is the aim to decrease it. So in the clear sky, we can talk about approximately 9% sameness in the LOC. So it means if we optimize, as you have seen, so we plotted for the solar multiple 1.1, 1.2, 1.3, 1.5, 1.7, as you can see here. And for that you can see that we get from this gain, solar north, 37% more heat over the year, and that is appropriated, this 9% appropriately. And definitely you can find in the table another one where you can see the breakpoint. You see this ratio. This ratio is going to be changed within the orientation. And also you can find here the LCOE for different positions. Definitely for solar multiple 1 would be this one the most attractive. How did it happen? Why we are calculating it? It should be known to everybody, and everybody knows, and everybody copy paste and say, so what's the new? New is that we have realized during our projects which we have been implementing, because we are doing the entire project development and also the entire supervision during the construction, and also we are guiding the operational personnel during the operation. And we realized, if you can see here in the morning, there was hazy. It was really hazy, but in the afternoon was clear sky. The reason was that we were close to the river, and you know, a river is holding water. So in the morning there was a cloud on the river, unfortunately touching our side. So, and then George was in Atacama Desert, and he realized that in the morning the weather is beautiful. But during the day, when the sun heats up, the wind is going to, turbulent winds is going to appear, which is going to take the sand in the air and make the weather hazy, as you can see here. So the opposite to the previous side. So definitely each desert has an asymmetric solar radiation, as you can see here, and that can be considered for the optimization. So we are still in the theory, and we are saying, well, you know this picture because you know there was the sun, there was the sun, there was the sun. Now in the morning we do not have the sun, so therefore the DNI could look like this one. If we plot it theoretically, there is no cloudy, clouds are disappearing, and finally all DNI is hitting our solar field. So we will gain the energy from this local time. This is a local time. That's so from 11 o'clock till 6 we will gain the energy, but not in the morning. Now we are going to plot all the orientation of the collectors for this case. So you can see this one disappeared because we are not operating, and we have only the part of this in the afternoon. And you can see how much we would gain if we have orientation east west, how much we will gain in north south, and definitely the best one is D1, which is going to face in the afternoon to the sun from this one, which is this dotted line, this red one. If we plot it into the frequency distribution load factor or in the annual solar heat, you can see that in the morning we definitely do not gain nearly anything. So we gain also less hours over the year because the morning is lost. In morning we do not have any heat, so therefore instead of 3,500 hours we have a less because the half of day we do not sun. Do you agree? Do you remember this one? We have a 3,500 hours to 4,000 hours per year sun irradiation. If we had the sun all the day, but in this case we do not have the day. We do not have it because we start with the sun irradiation late morning, close to noon. So therefore, these hours which are here, they will not be used for the production. So therefore, the reduction from 3,500 or 4,000 here to 2 or 2,500. Can you follow? Okay. And because we plotted it for the afternoon, that we in afternoon get more energy, because in the morning we are plotting this direction and we will be definitely zero, but in the evening we will get nearly 16% more. That was the theory. Now we plotted for you these lines based on the DNI data or meteorological data for the real side, which is the coast side in Gulf area, and you see you get some sun in the morning and in the afternoon. It is not absolutely theoretical that in the evening you don't have anything. You get some energy, but not so much. It is close to the sea, and therefore the effect with haziness in the morning is mirrored here. As you can see, it's a partially cloudy, as we shown here. And we are plotting all the directions. Again, this direction, this direction, this, and this. As you can see, definitely the most preferable would be D1, which is facing the sun in the evening, because in the evening we have the highest radiation. Now we are looking for the precise angle, because it's not only 135, it could be 112 or 115, depends on it where we are. Here we have the hours. For example, in this real side we have 3,000 hours when we can operate it in this position, and over 3,000 in this position. And if we put it oblique, we can see that in the evening we get nearly 2.8% more energy from the solar field over a year than if it would be in this position. And even if we do it in oblique in the wrong side, which is the risk of engineers, if you plot it wrong side, you can even get 2.9% less. You know, we talk about risk if it's the bearings by inclining the collectors, because it's the risk with the pylon and bearings. Here is the risk if the engineer does not consider it properly,